Hi everyone, we're excited to share our research, which comes from the Visual Computing Research Center at Shenzhen University, the City University of Hong Kong, and the Guangming Laboratory. The motivation of the paper. The aim of multi-view people detection is to detect the locations of people on the scene ground with multi-cameras as inputs. However, current methods have the following weaknesses. First, they are evaluated on small scenes, such as multi-view X and WildTrack, 20 meters by 20 meters. Second, some of them are not paying attention to the weight of each view, the rest of them using self-learned multi-view fusion weights. At last, the SOTA methods have relatively weak generalization ability to new scenes. Therefore, here are our solutions to the previous weakness. First of all, we evaluated the model on two large scenes CVCS and City Street with larger scene sizes, more frames, and views. Then we propose a supervised view-wise contribution weighting module without extra labeling for better multi-view fusion. In the end, we take a simple domain adaptation module for generalizing to new scenes. The proposed model is called the supervised view-wise contribution weighting model. This is its pipeline. It consists of 4 modules. The first module is single view feature extraction and projection. This module takes multi-camera images as input, extracts image features, and projects them onto the reference plane. In our paper, we take the average height plane, 1.75 meters, as the reference plane, and we get the projected feature maps. The second module is projected single view decoding. We feed the projected feature maps into this module, which predicts the single view probability occupancy map for each view. The third module is supervised view-wise contribution weighted fusion. This module estimates the weight map of each view based on the single view prediction probability maps and then sums it with the corresponding feature maps to obtain the fused feature. The last module is multi-view feature decoding. This module predicts the final prediction probability map of the scene. To obtain the ground truth, GT, of a particular view, the visible area mask of that view is multiplied by the scene GT. The City Street dataset is used as an example in the figure below, which displays the GT of 3 views in the scene GT. In this section, we will be discussing the important modules that we will be using. The first module we'll start with is the SVD module. As mentioned in the pipeline, we will be using the SVD module to predict the occupancy maps using the projected feature maps as inputs. We have already obtained the scene GT and single view GT by following the view masking process. At the same time, the SVD module has also predicted the single view occupancy probability maps. To train the model for single view prediction, we have used the mean square error function as the loss function for supervised learning. The formula for the mean square error function is as follows. Next, this is the core module of the proposed model, SVC module, supervised view-wise contribution weighted fusion. After passing through the SVD module, we get the single view prediction, and then we input the single view prediction into the SVC module, which is a lightweight CNN. We can use C to represent it. Then we can get the weight map corresponding to each view, and normalize the weight maps. Then multiply and sum the weight maps and the projected feature maps of the corresponding view respectively. Finally, the fusion features of the scene level are obtained. In the experiments, the statistical information of the 4 main datasets is presented in the table. It is noticeable that CVCS and City Street have larger scene sizes along with more people in the scene. In particular, the annotation label number, the scene number, and the view number in CVCS are significantly higher than the other datasets. We will now explain the comparison methods used in this experiment. 1. MVDET. This method projects feature maps onto the ground plane and then combines them by joining the features from each view. 2. MVDETer. This method utilizes the deformable transformer module to determine the attention weight of each pixel on the ground plane. It prevents distortion due to camera calibration errors. 3. SHOT. This method projects feature maps onto multiple planes parallel to the ground. It obtains the attention weight of each height plane to better combine features across different heights. 4. 3DROM. This method projects feature maps onto multiple planes and uses data augmentation techniques to prevent overfitting of training models on small datasets like Multiview X and WildTrack. It's important to note that the above comparison methods do not perform well on large scene datasets. The following are the evaluation metrics used in this experiment. These tables show the results obtained from the CVCS and City Street datasets. Based on the results, we can conclude that our method is capable of achieving a similar and even more accurate performance for ground location detection when compared to the state-of-the-art methods. We evaluated our method based on the F1_ score, taking the average rank as the evaluation standard. Our method is more stable and robust than the others, according to these metrics. The figure is the visualization results on CVCS. The 4 lines are the camera view input, single view prediction V_I, view weight I, and the final scene level prediction V_S of different methods in the corresponding scene GT. Our method accurately locates people on the ground compared to other methods, as highlighted in the red box. The figure is the visualization results on city state. The first 3 lines in the left figure are the same as those in CVCS. On the right figure, you can see the ground truth of the scene and the results of various methods. Similarly, within the red box, our methods demonstrate superior detection performance compared to others. Ablation study. First ablation study, without the Supervised View Wise Contribution Fusion, SVC, module. From the table above, it is evident that the SVC module achieves better overall performance, regardless of the backbone selection. Second ablation study, supervised, unsupervised, self-learned, view-wise fusion. From the table below, we can conclude that the SVC module obtains extra guidance for each view under supervision and delivers better performance, which indicates the criticality of supervision information. In the last ablation study, we conducted variable testing of camera numbers, using 3, 5, 7, and 9 cameras. The results showed that as the number of cameras increased, the metrics for MODA, MODP, and precision also generally increased. However, the recall metric decreased because, with more cameras, the model was able to detect more true positive cases with higher accuracy. But at the same time, the number of people who needed to be detected also increased, leading to more false negatives and ultimately causing the recall metric to decrease. Overall, the F1 score remained stable, indicating that the model is relatively consistent across changes in the number of camera views. Here is the domain adaptation method used in the paper. FT means fine-tune on the new scenes. A few labeled examples. DA means a simple discriminator-based domain adaptation module to reduce the real, synthetic feature gap. In particular, we add a discriminator in the trained model to reduce the gap between the training scene features and testing scene features. So, how do we do the generalization experiments? The model is first trained on CVCS, then we fine-tune it using 5% of the new scene training set images, RS, FT, then use a simple domain adaptation approach to reduce the domain gap to further improve the performance, RS, FT plus DA. The conclusion is that, with only 5% data, RS, FT, has a better performance compared with the methods in the first 4 lines, which are RCNN, POM-CNN, DeepMCD, and DeepOCC. When compared to other methods, the proposed method's cross-scene performance with unsupervised domain adaptation, RS, FT plus DA, is relatively worse. However, it is important to note that our method only uses 5% of the testing scene labels. Despite this limitation, the proposed method achieves a performance that is very close to other state-of-the-art methods that use 100% training set data and test on the same single scenario. As such, the results of our proposed method are still promising. The figure is the generalization visualization results on WildTrack. The visual test results in WildTrack for the CVCS trained model are similar under the RS, FT, and RS, FT plus DA techniques compared to other methods. The figure is the generalization visualization results on Multiview X. It has a similar performance as the one in the experiment of WildTrack. In the end, we conclude the contributions of the proposed paper. It is the first study on large scene multi-view people detection task with better generalization ability to novel unseen testing scenes with different camera layouts. We propose a new multi-view people detection method, which considers the supervised view wise contribution weighting for better multi-view feature fusion. At last, the proposed method's cross-scene multi-view people detection performance is promising compared to previous methods trained on the same single scenes, extending multi-view people detection to more practical scenarios. Our future work has 2 folds. The first is dataset expansion, meaning that we will explore larger, more diverse datasets to extend the method. The second is domain adaptation. We will create a stronger domain transferring module for better generalization. Thanks for your listening.